So let's get started here. Today's lab is going to be an introduction to our new, our next experimental technique, mass spectrometry. Okay, we're going to learn some background information, get some theory laid out, but then also we want to take some practical notes on how to go about analyzing these spectra here. All right. So when you set up your lab notebook, you're going to get your title. Make sure to put a date on there. All right. Leave some room for the purpose of your experiment, and then for some notes as well. I'm going to give a lot of background, but then I'll try to make extra clear what I want you to have in your notes section, because you're going to need it in order to analyze these spectra, something that we want in our notebook to look back on to make sure that we're doing it correctly. All right, so last class we talked about our gas chromatography instrument, right? And we looked at that data there. In particular, we looked at the area underneath the curves in our gas chromatograms. All right, and we said that the area corresponds to the amount that's hitting the detector. Okay, and that's all we kind of said, was that we had this detector that was like counting how many molecules were hitting it. This detector is actually this very fancy instrument, what's known as a mass spectrometry instrument here. Spectrometer. So, what does this thing look like? If we were looked inside this machine here, what happens is that we have this gas coming off of our column. Okay? That gas gets bombarded with a beam of electrons. All right, so again, your sample's making its way through the column. It hits the detector. This is how the detector works. The first thing it does is just blast your sample with a ton of electrons, a huge amount of energy. Okay? What that does, right, if we have our molecule here and we hit it with this high energy beam of electrons, what it does is it actually kicks one of the electrons off of that molecule, leaving it with a positive charge. All right, so we have our sample that's going through. We hit it with this beam of high energy electrons, and it kicks off one of the electrons from our molecule so that now our molecule has a positive charge. It also has this unpaired electron here, which we refer to as a radical. All right, we'll talk a little bit more about that here in a second. Okay, but the bottom line is that now our molecule is charged. Okay, so then it accelerates the ion. That part's not really important. What's really important is that what happens next is you pass it through this magnetic field here. Okay? Magnets interact with charges. This is something that's kind of complicated. You'll talk about it in your physics course if you get to that level of physics. But the bottom line is, like, a magnetic field can actually impart a force on an ion, right? So by putting these through a magnetic field, they're not traveling straight anymore. Now they're being curved by that magnetic field, right? The force of that magnetic field on that charge. Okay? The ability of that magnetic field to redirect those ions is directly proportional to the mass of those ions. So the really light ones, the teeny tiny ones, they get bent really far. They take like a sharp 90-degree U-turn, all right? The ones that are heavier, they don't get deflected as much, right? So they're only bent a little bit in space. So then at the end, we have this detector that's counting how many times it gets hit. And depending on where you are on that detector, we know the mass of that particle. Because the really light ones will hit on one side of that detector, and the really heavy ones will hit on the other side of the detector. And what's amazing is we're talking about down to the mass of a single hydrogen atom here, right? A mass difference of just one is enough for us to tell where this thing's going to hit on our detector. So we can figure out the mass of this compound down to like exactly whatever. We can differentiate compounds that only have a mass difference of one, right? So we can count. So basically we know exactly the mass of our particle that hits our detector. What's up?
So for that detector, I'm sure you would know this, but as you're saying it'll hit different parts of it. Is the detector split up into like sections that things should
It's like a line, kind of.
Okay. So
right? And over here is where the heavy particles hit. Over here is where the lightest particles hit. And anywhere in between there, I can tell how much that particle weighs because it got diverted a certain degree in my field.
Okay. But depending on what particles hit, like whatever that grouping is, it'll just be that
Correct.
Okay.
Yep. So this detector over here is literally just counting collisions. Boom, 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 boom. And it knows if it gets hit in one part, that corresponds to a very specific mass. Because if it was any other mass, it would hit over here. If it was a lighter mass, it would hit over here. If it was a heavier mass, it would hit over here. So if you're hitting right here, I know exactly what the mass of that particle is. Okay? So we bombard, bottom line, we bombard this thing with electrons. That electron actually kicks off an electron from our molecule, leaving it with a positive charge. Okay? And then we divert those ions in this magnetic field to our detector, and depending on where they hit, we know the exact mass of those particles. All right? So what happens is we get at the end, this is like a sample of zirconium here that was passed through, and you can see it can differentiate between every zirconium isotope. These only differ by like a mass number of 1, right? And I can tell the difference between all these different isotopes depending on where they're hitting at on my detector. Okay? Cool. So the first piece of information that we get from our mass spectrum here is looking at the very largest peak on our spectrum, what we call the molecular ion peak. Okay, we represent that as this M+, our molecular ion. Okay, so in our notes, let's start here. Analyzing the molecular ion. All right, your molecular ion, we're going to represent that as M with the plus, is the heaviest. We're going to add this caveat, or close to, and I'll show you why here in a second, ion on your spectra. All right, so when you look at your mass spectrum, it's going to look something like this. Let me just bring up a curve real quick. Okay, the one all the way at the heaviest end here is our molecular ion. All right, so if that was the only thing that we got on our graph, that would still be quite a bit of information, right? Because what's the mass of the molecular ion going to be? The molar mass of your compound, right? The mass of your actual organic compound that you have. So your molecular ion tells you the mass of your compound. Let's say the molar mass. All right, and that in and of itself is a large amount of information, okay? Because you can start playing with different molecular formulas, and if you're right, you add it all up, you should get the mass of your molecular ion, okay? So one of the things we're going to do here today is we have these unknowns from our IR lab. We have a good idea of what functional groups are in those unknowns. Using our mass spectra, we should be able to get the molecular formulas of those unknowns, okay? So, because we get the molar mass of our compound, which, you know, it's going to be a guess and check game. Don't get me wrong. It's not like there's one correct answer for your molar mass, but you can, from here, sort of predict your molecular formula.
So you're saying like the heavies are close to on the spectrometer or spectrum, so it's like towards the end.
Well, so, okay, so real quick, let's just look. Here's an example spectrum here. The values down here are the mass of the ions that are hitting it. And we'll talk about why this thing breaks up into a bunch of small pieces as well. All right, for right now, we're just talking about the big chunk, your molecular ion. All right, so that's going to be on your heavy end of your spectrum here.
So it's not the heaviest, but it has the most abundance.
We will see there's this other little guy right here, and we'll talk about what that is here in 1 second. Okay? So again, you can get your molecular formula, but it's like a lot. If all you have is a number, you're playing a pretty big guess and check game, right? So what other information can we get from that molecular ion? Well, first of all, let's just note sort of the differences between values that we would get. If we have no nitrogen atoms, right, so just carbon and hydrogens, we would get an even number for our molecular formula, for our molecular weight. And if we have a nitrogen atom in there, now all of a sudden we would get an odd number. Okay? And that's just because of the formula here. If you add this up, this would be C5H12. This would be C5H13N. All right, so if you have a nitrogen in there, you kind of have an extra hydrogen, which gives you an odd number. Okay? Likewise, if you had an oxygen in there, we can do the math. Let's just do the math. Let's see. So let's just do an example. C5, let's just look at an alcohol here. Okay? This is C3. How many hydrogens are in this here? Yeah. 1, 2, 3, 4, 5, 6, 7, plus that guy there. So H8O. If we want the mass of this here, we're going to take 3 times 12 plus 8 times 1 plus 16. And we get 60. Okay? So the bottom line is, what can we understand from our molecular ions? If we have an even number, that implies that we only have carbons or hydrogens, or maybe an oxygen in there as well. But if we get an odd number, we have carbons, hydrogens, and a nitrogen in there, right? So an odd-numbered mass ion, molecular ion, is an indication of the presence of a nitrogen ion, right? Something real quick we can see just by looking at that table. Okay? Now, absolutely, everybody's right to point out this little guy right here. Okay? The big one is my molecular ion. This thing right here is what we call the M+1 ion. All right, so where does that come from? Why do I have this M+1 peak here? Okay, so first of all, when I did the math for that alcohol, I said that carbon was 12. Why did I use 12 instead of the actual number on the periodic table, 12.0108? It's not that. It's actually not that. That number up there represents what? Is that only carbon-12 atoms? That's an average of all the isotopes that exist. But this detector is measuring single atoms that are hitting it. So it can tell the difference between a carbon-12 atom hitting it and a carbon-13 atom. It's not like this is on bulk anymore. We are separating out and looking at individual molecules. Right? So most carbon atoms in the world are carbon-12. But there is 1.1% of all carbon atoms that are actually carbon-13. And so they're going to contribute to this M+1 peak, right? You're always going to have a big peak for your molecular ion, and then a little one mass number up. This is for all the carbon-12s, and for this is for the small amount of molecules that contain a carbon-13, in the off chance that it does, right? Every molecule has a 1.1% chance of containing a carbon-13. Now, this is actually super powerful. We can use both of these peaks to get some pretty cool information here, all right? it turns out that the size of that carbon-13 peak, the size of that M+1 peak, will increase depending on the number of carbons a molecule has. The more carbon atoms a molecule has, the better chance that one of them is a carbon-13. Okay? So we can use the height of these two peaks to predict the number of carbon atoms in our molecule. Okay, so when we look at these graphs, we're going to have both a graph, but then we're also going to have a table of the values, right? If we grab our M+1 value divided by M times 100 and then divided by that 1.1% abundance of carbon-13, we can use that to predict the total number of carbon atoms in our molecule. Okay? So this is a great way. Again, your goal is to try to get your molecular formula, right? If you know how many atoms you have, that is a friggin' fantastic place to start, right? And so we can predict how many carbon atoms we have by looking at the relative height of these two peaks. All right, so this formula here is going to be a really important one as well. Let's make sure we have that in our notes. All right, so if we're comparing our molecular ion and the M+1 peak, we can use that to predict the number of carbon atoms. All right, and we'll do that here in a second with our example spectra. But again, that formula is that the number of carbons the M+1 peak divided by the M peak times 100 divided by 1.1. And again, that 1.1 is the abundance of carbon-13 here on Earth. Now, I gotta say, we're gonna be looking at real data, and in no way, shape, or form do you like always get a nice, neat whole number. Like, it's not gonna work out to be exactly 4. But it's gonna be like 4.2 or something like that that you can use to approximate what it is. Okay, so again, our molecular ion, it's going to be the one that's on the far end of your spectrum here, right? It's going to be the molar mass of your compound, which is already in and of itself quite a bit of good information. Okay, we can look at the value of that number. If it's even, we know we have carbons and hydrogens and maybe an oxygen. But if it's odd, we know we have a nitrogen atom in there as well, so that's a pretty good indication that there's a nitrogen. All right. And then we can go even further by looking at the values of that molecular ion and the M+1 peak and use that to predict the number of carbons. Okay? Cool. Now, we are not just getting, if we go back to the spectrum here, we are not just getting 2 peaks, right? We don't just get the M and the M+1. There's all this other crap down here as well, right? So where does that come from? Why do I have so many different lines on this spectrum here instead of just 2? Well, we said that when that electron bumps off that other one, we get what we call a radical cation. And this name is so radical because this thing is very unstable. Okay, so these radicals aren't happy. We have an unpaired electron. It's furious. All right? Maybe it survives all the way to the detector, but there is a large population that is going to just start breaking apart. It's just all sorts of mad. It just starts collapsing. All right? And so that's why we get our big peak at the very end of our spectrum corresponding to the whole intact molecule, but we also get a bunch of little fragments as well. What happens is our radical cation will break up into an uncharged radical, so something my detector isn't going to see, right? It's just going to fly right through that magnetic field without being diverted, and then a smaller carbocation fragment, right? So that radical cation that's formed isn't always going to be 100% stable. That's not the only thing that's going to make it to the other side. It's going to start to fall apart, which is why we see little pieces along the way as well. Okay? So let's look at for pentane, for example. Where is my molecular ion in this here? So the molecular ion, all the way down at the large end of the spectrum here, right? It's actually quite small. There is not very much intact pentane that makes it to the end of this detector. There's a small amount. I do see my molecular ion peak. The molar mass for pentane is 72. Okay, so that's my molecular ion that I see. I also have a tiny bit of that M+1 peak as well. But most of what's making it to the end here is stuff that's fallen apart. Okay? And we see that they're kind of clustered, right? I get one group of peaks here, one group of peaks here, one group of peaks here, one little group of peaks there. Right? So why is that? Each one of these little clusters corresponds to a carbon fallen off. Right? If I take my methane and I chop off that last carbon, what would be the mass of that fragment? I would take my molecular ion and I would have to subtract what? What would it be? What would I be taking off to take off a methyl group there? Carbon and 3 hydrogens, which is 12 plus 3, 15. All right, so what often happens is we see this little like spaced out pattern here. This cluster here is going to correspond to the M-15 group, right? Losing a methyl group. So M-15 means we lose a methyl group. What happens if I chopped my molecule right here? What would I be losing? 2 carbons and 5 hydrogens, right? So if I did the math on that one, that would be my M-29 peak. 29 plus 14. If I lost one more, that'd be my M-43 peak, etc., etc. And then this one, I guess, is just that methyl group, right? So whatever, 72 minus 15, what do we say that is? 57. Right, so now I lost an ethyl group, I lost a propyl, and I lost a butyl. Right, so again, you do get some amount of intact molecule, and it's very molecule dependent. Some molecules are much more stable as radicals and make it all the way. Just like benzene, you get this massive molecular ion peak here and very little of the small fragments. Other molecules are much different. They fragment much easier. And we see this sort of pattern here where we have a bunch of peaks corresponding to when one methyl group falls off. 2. Now, there isn't just one peak. There's a few other ones here. Sometimes a single hydrogen atom will fall off, right? That would be a mass difference of just one. But they tend to group in these patterns here. Okay, so this is all well and good. Sometimes it's really hard to analyze these fragments and really make sense of it. The good thing is that each molecule will produce a distinct pattern. And so much like we were talking about with our fingerprint region of our IR, it's like, all right, this is really confusing. I don't really know what to make of this. But you know what does know what to make of it is a database where you can just put your spectrum in a search engine and it matches to a bunch of known molecules because they will fragment in this very specific way. Okay? So for us and our pencil and paper purposes, this molecular ion by far has the most information, but these fragmentation patterns are distinct and there is still a large amount of information in there as well. Okay? All right, so then that takes us to kind of our worst case scenario here. We have some very ill-behaved molecules. All right? This M+1 divided by M business, awesome, right? That works great. But that only works if you have a molecular ion in your spectrum. Okay? Some compounds are so unstable as radical cations that they'll produce any amount of these here. And the one big one that we want to address, because it's pretty important to our course, are alcohols. Alcohols are a son of a gun in the mass spec. They never, I don't want to say never, they very rarely survive as molecular ions in our mass spectrum. So we're often trying to make sense of just the fragments, not the end one, right? We can't do our number of carbons prediction with our alcohols. Okay? So if we have an alcohol, we got to be a little bit more careful in analyzing our spectrum. Okay, so we could say if we have our molecular ion, great, fantastic. Okay, but often we do not. You know, or maybe it is in your spectrum, but like the peak height is like so small you don't even really see it on your graph. It gives you some tiny number that pales in comparison, right? It's just got too much error. So not present or very small, which means we're not going to get a reliable prediction out of it. Okay? We still can kind of make sense of that here. So, if we have what we call a primary alcohol, meaning our OH is bonded to a primary carbon. All right, we talked about that here today. How many neighbors does that carbon have? Just one. Okay, so for primary alcohols, we might not see the M peak, our molecular ion, but we will see the M minus 18 peak. This right here corresponds to a loss of water. All right, 18 is the molar mass of water. So it turns out that what happens is this OH group right here gets super mad and flies off, but it ends up taking a hydrogen with it. So it comes off as water. So for primary alcohols, you almost never see that molecular ion peak, but you do have a nice big peak at M minus 18. So the peak that you do see, you add 18 to it, and that would give you your molar mass of your compound. Okay? That's for our primary alcohols. Okay, for other alcohols, secondary or tertiary. All right, so I'll just do an example of each. So secondary OH on secondary carbon. Tertiary means the OH is on a tertiary carbon. These actually break up a little bit differently. Okay? So again, we might not see so in this case, the oxygen doesn't come off, but like what happens is that the oxygen's unstable, so it cuts off one of the nearby carbons. Okay, so instead of seeing the oxygen and two hydrogens come off, we see a methyl group come off, or an ethyl group come off. et cetera, those groups that we just talked about, right? So a loss of a methyl group, that would be M minus 15. The loss of an ethyl group would be M minus 29. The loss of a propyl group et cetera, et cetera. Okay? So this is definitely playing it on hard mode here. Now we're trying to make sense of what we see in the middle of our spectrum here, right? We don't have our molecular ion peak, or maybe we do, but we really can't get much information of it because it's so teeny tiny small and kind of in the weeds. All right? So instead, we have this information here that alcohols will fragment differently, whether they're primary versus secondary or tertiary. Okay? If it's a primary alcohol, it's going to lose a water, so a mass of 18. So I could look at that peak and add 18 to get my molar mass. If it's a secondary or tertiary, I would add one of these values here to get to my molar mass. All right, so then how can I differentiate? What do we notice about the difference between losing a water and losing, let's say, a methyl group? 15 versus 18. Okay? It's definitely going to be towards the end. They're pretty close, though, right? So first of all, though, let's remember, if our compound is an alcohol, it only contains carbons and hydrogens and oxygens. What should my mass number be, even or odd? Should be even. And what's the difference between losing a primary versus losing an OH group, or I'm sorry, geez, I just botched that. Losing a water from a primary alcohol versus losing a methyl group from a secondary alcohol? I'm subtracting an even number versus subtracting an odd number, right? So I can start playing around with these numbers. I know my mass number has to be even, right? Because it's going to be an alcohol. So if I add 18 to it, does that give me an even number? Yes or no? If it doesn't, if I add 15 of it to it, does that give me an even number? All right, so that's how we can sort of figure out what our alcohol is. Alcohols are the pain in the butts, right? It's awesome if we have the M and the M plus 1. Done, right? If it's going to be a little bit more complicated, though, we got to get in the weeds there. And again, alcohols are going to be the one that we see most often with this. Okay? So everybody take a second. Let's get a computer ready. We don't need Excel today, but all of our data that we're going to be analyzing is on the computer, on Canvas. So take a second to get all set up. Okay, so most of our, well, all of our analysis, all of our spectra are going to be online, but I'm going to be grading in your notebook. Okay, so we're going to do this one together where we go through hexane. We're going to predict the molar mass of this compound by looking for our molecular ion. We're going to predict our chemical formula by doing our number of carbon calculation. Okay, and then lastly, we can predict our compound identity. I'm going to tell you it's hexane, so it's not going to be that interesting for this particular one. But we got a bunch of different spectra that we're going to be analyzing, and this is what I want to see in your notebook for each one. Okay, so let's do hexane together first.